Good morning, students. This is K. Lakshmi, Assistant Professor in the Department of EEE, Chebrolu Engineering College, Lecturer 45, Unit 5, Time Varying Fields. Topic: Faraday's Law of Electromagnetic Induction. Before we discussing about the Faraday's Law of Induction, let us discuss about the basic definitions. Magnetic flux. Magnetic flux represents how closely together magnetic field lines are packed. Generally, magnetic field is expressed in terms of magnetic flux lines. The magnetic flux lines are indicated by the letter phi, and B is called magnetic field intensity. Now the relation between magnetic flux and to the magnetic flux density B is expressed as phi is equal to A bar dot B bar. Here A is area of the plane and B is the magnetic flux density. Here theta is the angle between area and to the magnetic flux density. So the magnetic flux is more, that means it indicates the magnetic field is strong. That means whenever the strong magnet means it consisting of more lines of flux. So here the magnetic flux phi m is expressed as A dot B. Here A is area and B is a magnetic field intensity. So theta is the angle between A and B. So phi m is expressed as AB cos theta. The units of magnetic flux is 1 Weber and it is also expressed as 1 Tesla meter square. The graphical representation of magnetic flux lines. That means when you observe these two figures, the first figure indicates this is the plane. The magnetic flux lines are passed through this plane are more. That means it is a strong magnet. The magnetic flux is proportional to the number of flux lines passed through this unit area, and you observe that this surface is taken as a perpendicular to the magnetic field lines. So whenever more flux lines are passed through this surface area, then it has more flux density. That means the flux density B depends upon the total number of flux lines passed through this surface area. According to Gauss law, an electric current creates a closed wire loop when it is moved through a magnetic field. An arbitrary shaped surface can be placed through the loop and flux is calculated by the expression phi is equal to integral B bar dot ds. To calculate the magnetic flux in a non-uniform field, it is expressed as phi m is equal to integral B bar dot dA. Here dA is small area which flux passing through this little area, then simply it is expressed as a d phi m is equal to b bar dot dA. To calculate the total flux, simply integrate on both sides, then this expression is converted as a phi m is equal to integral b bar dot dA. Now today we discuss about an important topic, that is Faraday's law. So before we discussing Faraday's law, we have to know the basic definitions of magnetic flux, magnetic flux density, and the relation between magnetic flux to the magnetic flux density. That means phi is equal to integral b bar dot dA. Now almost 200 years ago, in 1831, Faraday give the evidence that a magnetic field would induce an electric current with this experiment. Actually, in the previous chapters, we discussed about the static electric field or a current carrying conductor creates a magnetic field. Here it is an opposite to that. That means a magnetic field creates electric current. So that is the main concept. So this is the experiment we have to use for Faraday's law. So this experiment consisting of apparatus, magnet, coil and galvanometer. So the Faraday's experiment, no evidence when the magnet was stationary. That means a static magnetic field cannot induce electric current, but a time variable magnetic field creates an electric current. So when you observe these figures, the first figure, it is a magnet and the coil is connected to a galvanometer. Galvanometer is useful to measure the determination of smallest values of current. So here, whenever a magnet moves towards the coil, when you observe this figure, the galvanometer shows some deflection. The second figure, when magnet moves away from the coil, the galvanometer shows a negative deflection. The third figure gives, if there is any no momentum in the magnet, that means when the magnet is at stationary, so in the galvanometer the position of the is at 0. That means there is no deflection in the galvanometer. By observing these all figures, whenever magnet move towards the coil, that means more flux lines are passed through the coil. So due to that, an induced electric current is developed. That means it shows the evidence of a time varying magnetic field induced an electric current. That is the conclusion of Faraday's law experiment. So here the very important point is, static magnetic field cannot create electric current. Only the time varying magnetic field creates an electric current. So whenever we discuss in the previous chapters, we only discuss the static electric field and static magnetic field only. But in this topic, we discuss about a time varying field. That means whatever the field, that is whether it is an electric or magnetic field, the values, the magnitude of the field will be changes as time to time. So that's why these fields are called time varying fields. The important conclusions of Faraday's law is: galvanometers show deflection whenever there was a relative motion between magnet and to the coil. That means when we move towards the coil, then galvanometer shows some deflection. And whether the magnet move away from the coil, again galvanometer show the negative deflection. That means galvanometers show deflection by the motion between magnet and to the coil. And the deflection was more when the relative motion was faster, and it will be less when the relative motion was slower. And also the direction of the deflection in the galvanometer changes if the polarity of the magnet was changed. Polarity means the poles. By changing of the poles north and south, automatically the deflection direction is also changes. And also the deflection in galvanometer changes with change in the number of turns of the coil. That means more the number of turns, greater will be the deflection. So these are the important characteristics exhibited in Faraday's experiment. Now, Faraday's law of induction. So this is simply a self-induction. That means moving the magnet changes, the flux is changed. So here there is no battery here, there is no power supply here to this coil, but even though due to movement of magnet, here the EMF is changes. Here it is an example of mutual inductance between the coils. So here there are two coils are there. Now if we connect a battery to any one of the coil, automatically a magnetic field is developed. Here we use an alternating current. That means there is a changing in current, so automatically in magnetic field is also changes that takes place. So here that indicates by delta I by delta T. Due to changing the current, the flux is also changes. So the variable magnetic flux, here an electric current is developed in the second coil. So simply Faraday's law means change in the flux induces an EMF. That means EMF is expressed as a delta phi B by delta T. That means the EMF induced around any loop is equivalent to rate of change of the flux passing through that loop. So this is the simple explanation of Faraday's law of induction statement. Now, the induced EMF in a wire loop is proportional to the rate of change of magnetic flux passing through the loop, and magnetic flux phi B is equal to B dot A. That means BA cos theta. Now the unit of magnetic flux is Weber. So the induced EMF is expressed as a del phi B by delta T. So it is applicable for a one loop. If in the coil consisting of n loops, then the induced EMF epsilon is equivalent to minus n del phi b by del t. Lenge's law. Faraday's law gives the magnitude and direction of the induced EMF, and therefore the direction of any induced current also. Lenge's law is a simple way to get the direction straight with less effort. That means this is easier to use than to Faraday's law. Decrease the magnetic flux, EMF creates additional magnetic field, and increase the flux, EMF creates opposite to the magnetic field. So simply, Lenge's law means the induced EMF is directed so that any induced current flow will opposes the change in magnetic flux. So here these two figures are indicates the how the electric field is developed. One is created by a charge. Here we have to take in a positive charge, and another one is created by a magnetic field. So these circular rings are simply magnetic field, and the into mark is indicates the electric field. Now, the self-inductance, already we discussed in the 4th chapter. Again, here I just recall that the effect in which change the current in a circuit induces an EMF in the same circuit, which is referred as self-induction. In the similar manner, self-inductance expression E is equal to minus L del I by del T. Here del I by del T means variation in current which creates the change in magnetic field. So due to that a self-inductance is developed. So that self-induced EMF E is expressed as a minus L del I by delta T. Similarly, the changing current in the primary coil. So this is the primary coil. So here we connected to primary coil to an AC generator that indicates alternate current. Whenever an alternate current is applied to primary coil, it induces a time varying magnetic field. This time varying magnetic field creates an induced EMF in the secondary coil. This induced EMF is creates, that means a current in the secondary coil. This induced EMF is nothing but voltage. So here we connected to is a voltmeter to the secondary coil. So with the help of voltmeter we can easily measure the what is the induced EMF developed in the secondary coil. So this effect is called mutual induction. So mutual induction means due to passage of alternate current in the primary coil creates current in the secondary coil. So this is expressed as a E is equal to minus N del phi by del T. Here the term del phi by del T means rate of change of a flux. That is the very important point. So these fields are time varying fields. And mutual induction ES is equal to minus M del IP by del T. Here IP is the current passed through the primary coil. So the units of mutual inductance is Henry. Thank you.